we are working on 3D. Right? And I'm going to be showing you a piece of software to help us out, but just to kind of do a quick summary. Did anybody figure out, is that called the left hand or the right hand drill? Does anybody know?
I remember it as the right hand roll.
Okay, so it's the axes are orientated on the right hand drill. So that guy in the ground there is called the XY plane. This guy here on this wall is called the XZ plane, and I'm not sure the colors. And this guy here is called the YZ plane. And didn't we talk about how you can tell if a point's on the X, Y, or Z axes, and how you can tell if a point is on the X, or Y, or Z plane? So let me just test you on that. Is that, tell me what that point is in. Tell me either the line, X, Y, Z axis, or the plane that that point is in.
X, Y, X, not axis, plane.
So you said, if I picked you up right, that this point is on the XY plane. Agreed?
Yeah. We can't see the.
Oh, disappeared?
At least for me it did.
Yeah, well, probably didn't for everybody. Let's figure it out. There we go. Are we back? Right. Wasn't the clue the thing that's missing? And by that, I mean the 0. So if there's a 0 on the Z and you have 2 numbers, doesn't that make it the XY plane? What would this be? Where would that guy be?
X-axis.
Okay, correct. How would you tell? How do you know just looking at it?
It's kind of wherever the value is. So
Right.
if it's on the X and nothing else, then it's on the X.
That's it. And the Y has a similar shape and the Z has a similar shape. So what we're trying to do is just get you used to coordinates and where they are in relationship to the X, Y, Z axis or these 3 planes, as we know. Now, if I ask you questions and they do in the homework to tell how far, right, the shortest distance, and I said to you, I would like to know how far this guy is from, say, the XY plane, and then the XZ plane, and then the YZ plane, right? So can you imagine the point 1, 2, 1, 2, -3, kind of be here. I know you can't really see it, but they're kind of down there. If you want to know how far a point is, right, from the XY plane, how far is it? How do you tell? Simply by knowing its coordinates and nothing else. Yeah. 3. And you get it from here, don't you?
Mm-hmm.
And distances are whole positive numbers, so that's 3. If you wanted the XZ guy, so I'll put the fella here now, and you wanted to know how far away this point is from the XZ plane, wouldn't it be that number? And if you wanted to know how far away it's from the YZ plane, wouldn't it be that number? So if you want to know how far a point is from one of the 3 walls, right? I'm just calling these the walls, right? From one of the 3 walls, isn't it the coordinate of the thing that's not mentioned? So if it's the XY plane, it's the Z coordinate. If it's the XZ plane, it's the Y coordinate. If it's the YZ plane, isn't it the X coordinate? Knowing that doesn't make these questions pretty easy, but it's something you just got to remember, right? It's just a property. I mean, if you didn't do that, I guess you could try and draw it, but God, I don't know if that would help much. Now, there is one more of these, and then I'll show you some software. I'm going to look at the point 1, 2, 3, and we want to know how far it is from the x-axis, how far this point is from the y-axis, and of course, how far this point is from the z-axis. That's going to be a bit trickier, because to be able to answer any of these questions, I have to introduce a formula to you, and it's called the distance formula. Now, there is a distance formula for two-dimensional objects. There is one for objects in 3D. So suppose I want to find the distance from the point P with coordinates x1, y1, z1, and I want to find the distance to Q, which I'm going to call x2, y2, and z2. Just thought process came to me. Do you know if it's two-dimensional? I hope you've seen this somewhere. It's called the distance formula. You ever seen it? How you find it? Right. You can extend that to 3D. Now, that's the formula for the distance between 2 points in 2 dimensions. What do you think the distance formula for 2 points in 3 dimensions would look like?
Well, you have to add z, and then so you just get a third section of squareds.
Yeah. Now, what makes, to me, I don't know if it makes it to you, but to me, what makes that fascinating is that now that I've got this kind of generalized growth, couldn't I find the distance between 2 points in 4 dimensions? Even although I haven't a clue what that means anymore. Right, I can visualize 3, right? That's as good as my brain is going to take me, right? The distance from that tip to that tip, yep, it's a number, right? What we call scalars, right? It's a scalar. Couldn't I do the distance between 2 points in 12 dimensions? Right? There's no limit to it. Which kind of means to me then that isn't mathematics powerful? That it can do things that you even don't know what they look like, but you can still do them. Right? I can still find the distance between points in any dimension. Right, so that guy there is going to get used. So if I want to know the distance this point is from the x-axis, what I need to know is who the other point would be. Who is the point on the x-axis that this guy is closest to? So if you do point 1, 2, 3, what point on the x-axis would be the closest one to it?
Be 1, 0, 0.
And in this one, which point would be closest to it on the y-axis?
0, 2, 0.
Are you beginning to see a pattern, guys? And in the last one, then, which point would be closest to it on the z-axis would be that guy. Are you with me? Now, I won't do all 3. Which one do you want me to do? The shortest distance to the x, the y, or the z? Just so we can use this formula once. Don't want to do it 3 times. Any preference?
It looks like x would be the easiest because it's all zeros and ones.
Well, yeah. Okay. So we're going to do P, which is 1, 2, 3. We're going to find the distance to Q, which is 1, 0, 0. And the distance formula says, I won't write that again. It says, oh, I might put this one at x1, y1, z1, x2, y2, z2. Let's see what you get. You get 1 take away 1 squared plus 0 take away 2 squared plus 0 take away 3 squared. And that gets me nothing squared, 4 and 9. So I get the square root of 13 and leave it alone. We don't want decimals. Hopefully I've added that up right. So are we comfortable about shortest distance to an axis?
Couldn't we use Pythagorean theorem too? Because technically, once you get it to an axis, you're only
Yeah.
working in 2 dimensions.
If you did it, you would end up with the exact same answer. In fact, the proof of this comes by using Pythagoras' theorem. So it's really just putting Pythagoras' theorem into a formula, but that's essentially where it comes from.
So on a test, would we have to use the distance formula, or could we use Pythagorean theorem?
Mind. If you think the distance formula is easy in your brain, you can do it that way. If I'm picking you up correctly, you're basically saying the distance from 2, 3, 0, 0. Is that what you're saying? Yeah, that makes perfect sense. Yes, that's okay. So imagine I told you to sketch that guy. Well, in the 2D world, so this is back to 2D world for a minute. X equals 1 is a vertical line of points, isn't it? But in the 3D world, X equals 1 are all the points in 3D space that have the property that their X coordinate is 1. What on earth does that look like? You got to try thinking 3D here. I know it's hard to draw it, but imagine all the points whose X coordinate was 1. That means their Y and Z coordinates could be anything they like as long as the X coordinate is 1.
That'd just be a plane.
Right, what we call a plane. I'll call it a wall, but you're right, plane is a better term, right? When you get a wall, would it be a vertical or a horizontal wall? I'm just trying to do it in the language of visualization. Would it be a vertical wall or a flat wall, like a roof ceiling kind of shape? Vertical. And where would it be? Well, wouldn't it be wherever X equals 1 is? And so it would look something like this. Can you see why you should try never to draw 3D shapes on 2D paper? So let's show you how you should visualize it without drawing it. So here is a guy that's hidden. So let me find the guy. There we are. I'll move it over here. Can you see a graph called GeoGebra in front of you right now? No. Okay, so I'm going to go back out and find that guy. There. Can you see it now? Right. This is a nice piece of software. It's in Canvas, and it's called GeoGebra. I think it's the third one in the list. Desmos, did the parametric stuff that we did. There's a guy in the middle. Don't worry about him right now in this one. Now, the way it works is pretty easy. You just go here and you type X equals 1 in. And if you rotate this thing, so you hold your mouse on it, isn't that kind of cool? And if you move it, you can move in. If you move your little thing, you can change your scales. And X equals 1. Now, let me rub that guy out. How about X equals 5? And go in a bit. Yeah, there's X equals 5. And let's do X equals 1. And let's do another one with negative. Let's do X equals -2. Do you notice something about those 3 lines? Do you see this? The orientation I've got right now, I think it's back to front, so I'll rotate it this way. There we go. The red line is the x-axis. So I'm just walking around the building and looking at it from a perspective. Can you see the vertical plane at x equals 5, the vertical plane at x equals 1, and the vertical plane at x equals -2? Isn't that kind of cool? That you don't need to draw it, you can visualize it. Okay, let's take a couple of these guys out if I can. That's that one. Let's take this one out. I should just be able to kill these guys, shouldn't I? There we go. I'll keep one of them. Let's put equals 5 back in, right? What do you think y equals 5 would look like? Vertical or horizontal? Y equals 5.
It's gonna be vertical, but like on the other axis on the y-axis.
Right, so
on the
it'd be perpendicular to that, right? Like a front wall and a side wall. Being totally non-mathematical. I forgot what number I did, so I'm putting in 5. Are we comfortable with that? Yeah, kind of cool. And let's do z equals 3. Can you see z equals 3 is like a ceiling? In fact, do you know my analogy of walls kind of works well here, for me, visually, because I'm a visual person. Any line that is the form of a single variable, x, y, or z equals a number, don't you either get a vertical or a horizontal plane? That's what they look like.
Can you make
And
this thing graph an inequality?
I have never tried.
I mean, if you could make a pretty cool house.
Oh, okay. I've never tried. You can have fun with it there. Right, try to get rid of these guys. Now, in 2D, isn't y equals x a straight line, a diagonal line? Right, in 3D space, y equals x looks like that guy. For want of a better word, it's a diagonal wall, isn't it? I would probably call it a diagonal, right? A plane. Now, what does x plus 3y minus 2z look like? Right? Well, if you put them equal to a number, fingers crossed this will work. Yes. You get a sloping plane. We call that all those different combinations of linear combinations of x, y, and z. They're all called planes. A plane is just a flat piece of paper that goes on for eternity, right? And that's orientated in a particular way. Suppose you wanted to visualize. Right, y equals x squared. Would you agree that's a big happy face in 2D? Any predictions about y equals x squared in 3D?
Going to be a curvy wall.
And if I, oops, I'm losing it. Okay.
So we made the bow of a ship.
We did, in a way. Yeah. But can you see that if you want to design something in 3D, couldn't it be made up of bits and pieces like planes meeting quadratics? Now, I'm pretty sure that most ships aren't x squared, but I don't know enough about ships. Maybe that's a really nice curve for the bow of a ship to be, but it's probably more complicated than that. But can't you do that? There's machines, I'm going to waste the name of them, but they're numerically controlled machines where you can actually program them and they will machine various 3D shapes for you. A bit
CNC
like
CNC machines?
CNC machines, right? Can't you also do 3D printers? So if you're doing a 3D printer, wouldn't it be useful for you to program in the equation of the 3D surface, or at least the outside of it, in a way that would make it easier for that machine to interpret?
This
So-
is something I actually used to do for a living, and yeah, that is a lot of it is how we do it in a thing called G code. So you'll have G commands, G sub zeros to go home, and you'll enter an equation, and they can actually cut to that, or you can generate like a whole pattern. So you can say you want 6 holes evenly spaced on a circle of 6 inches, and it'll punch those 6 holes at 60 degrees off of each other.
hey, we're doing stuff that actually gets used. It's just kind of boring for me, but not for you lot. I'm
No,
losing interest in this because I like it because it's just fun. But I can imagine a lot of you are not going to become mathematicians, and I understand that. But it's kind of cool, isn't it? 3D. If you orientate it a particular way, in other words, it's kind of hard to. There we go. If you look at it from a certain way, can I do that any more or worse? Oh, I made it go away. There. There's a kind of sweet point that I'm about to get to. Can't you see the y equals x squared shape? And it's basically just projected along the z-axis. You can make it go any way you like. Suppose I did z equals x squared. What we now have are two different, if I can orientate that, there we go. Don't we now have two different, there we go, shapes interacting with each other? One is going this way and the other's going that way. So any basic shape that you want, can you imagine that you don't need to try and draw it on paper? You can just go to GeoBra and have a good look at it. I think that's kind of cool. That's the kind of thing you can just play about with and have fun. But it's a tool that I think is helpful if you want to see what the heck what you're doing, right?
You were talking about having more than 4 axes.
Yes.
CNCs actually do that. They'll have like 5 to 7 axes. But unfortunately, anything over 3, what you're actually getting is you're either tilting the part left or right, rotating the part in a circle, or you're rotating the head of the cutter, rotating the head that has the cutter on it, left, right, in and out, at an angle, etc.
Right, and in that sense, they're calling them dimensions, but really they're just shortcuts for one of the other 3 dimensions being used together.
Yeah, exactly. I just wanted to ruin anybody's fun who is thinking about that.
Okay, let's see. I'm drifting because my poor brain can't focus. There's a surprise, me not being able to focus. So let's show you what some of your homework questions look like, because we haven't really done anything as far as I can tell. So here's a question where they give you 3 points, and the first one says, which is closest to the YZ plane? Well, wouldn't you just look at them and find out how far away each one is, and the one that had the smallest number would be the answer. So which one of those is the closest to the YZ plane?
It'd be C.
And the reason for that is that it is 1 unit
Only
away.
one.
No, 1.
And this guy is 4 units away, and isn't this guy 3 units away? Remember, we did that at the start. So that's how they would ask a question that would involve us using one of those things that we wrote down there, right? So here is a point. What would happen to it if you projected it onto the XY plane? Well, wouldn't it turn into the point 3, 5, 0? Agreed? If you take a point and you project it onto the XY plane, don't you just make it Z coordinate 0? And there's some pictures of it happening. Don't know how good they are. Now, what does the line x equals 7 look like? Well, we just did that similar question a few minutes ago. And we call that shape a plane, don't we? And think this here is very similar to GeoBra, but it's kind of primitive and a little bit ugly. Would you agree? But you could use it if you wanted to. Now, what would this guy look like? Well, if you put it in GeoBra, it would be a sloping plane. And this is the set X, that guy Z. I'll let you play with that. I'm not going to get into that one. Okay, wouldn't question 5 just be use the distance formula and the root square root of 17? Oh, this is good. Writing this down. This is question 6. And we are going to do some really cool math with 3D. We're being asked to find the length of 3 sides of this triangle. And this triangle is being drawn in 3D space. So first thing is, I'm not going to make any attempt to pretend that this is accurate. I just want you to imagine that these are placeholders for P, Q, and R, right? Just something to visually draw, right? In 3D space. Now, when you write down that in mathematics, it looks like it's the absolute value of PQ, but doesn't it mean in the context of this, the length of PQ, right? The distance from PQ. And so you would be using the distance formula. And then we'll do PR, and then we'll do QR. And if you do PQ, the answer is 2 squared, 2 squared, and 1 squared, which is 9. So that gets you 3. If you do PR, it's 2 squared, 4 squared, and 4 squared. 4 squared is 16, 16, and 4, which is 36. And if you do QR, it's nothing, 6 squared and 3 squared. And 6 squared is 36 and 3 squared is 9. So it's square root of 45, which I could redo as 9 times 5. 9 becomes 3 root 5. So these are, PQ is 3 units, PR is 6 units, and QR is 3 square root of 5. Are you happy about that? And if I've screwed up with the adding, you can tell me. So far, so good. Right, now, is this triangle right angled or do you spell isosceles or isosceles? And it could be no in both cases. So how do you test? Well, although this shape started off in 3D, when you join 3 points of a triangle together, don't you now just have a 2D shape? So think 2D again. Is this triangle right angled? Yes or no? I got a thumbs up, which is correct. It is. Prove it to me.
I used the Pythagorean theorem. And so I took the smallest, I figured that 3 root 5 is greater than 6. So if it is right, that has to be a hypotenuse. So I just tested a 3 squared plus 6 squared, and sure enough, that equals 45, which square root is 3 root 5.
Right. So essentially, he's using, it's called the converse of Pythagoras. It basically says if the biggest 1 squared is equal to the other 2 short 1 squared, and I'm using these numbers because they're easy to work with, would you agree that's 45 and these 2 squared and added are 45? That makes it yes. It could also be at the same times be isosceles. It might not be, but it could be. Is this one isosceles? I see a shaking of the head, and this is correct. Prove it to me.
The only isosceles, because it's right triangled, the only isosceles triangle it could be is a 45, 45, 90. That would require that 2 legs be equal, which they're not.
Right. So if you're going to get isosceles, don't you need 2 sides to be the same?
You do, because you need to have all internal angles out of 180 degrees.
Right. So that's a no. If it was going to be equilateral, wouldn't you need all three sides to be the same? But if it's equilateral, it's never going to be right angled. There's two contradict each other. Right. Well, that was the example of that question. Now, the next question has a fancy name, although this book doesn't use it, but I'm going to use it anyway because I like it. And that term is collinear points. So we are talking 3D here, even although I'm drawing it on 2D paper. Can you imagine these are 3 points? I'm calling them P, Q, and R. And collinear points mean that all 3 points lie on the same straight line. And you're going to be given the coordinates of 3 points. So this is question 7. And the points are 2, 3, 2, 3, 4, 1, and 1, 2, and 3. Okay. Now, how do you prove that 3 points are collinear? Because the answer is just going to be yes or no. So I don't want you to just say yes or no, because you could say yes, and if it's wrong, you'll say no, and the question's over, right? It's easy to do as homework, but we want to be able to do it, not just, you know, randomly guess till we get it right. So we're going to do it with distances. And I've just called that A, B, and C, and P, Q, and R, so I better rename my lettering. Right, A, B, and C. Now, I'm going to find the length of AB. I'm going to find the length of AC. I'm going to find the length of BC. And I'm not going to find actually these ones because I want you to do it because there's not much chance. Can we pretend that this ends up being 9? And this ends up being 3. And this ends up being 6. They are collinear. What is the property that I'm looking at, or how do I tell by just looking at those 3 answers that they are collinear? Because remember, these points could have been in totally different. Couldn't A be here and C be here and B in the middle, right? So don't pay too much attention to where they are on the line. Focus just on these numbers.
Well, you could take the equation for the line that they form by going, you know, x1. So slope is rise over run.
Yeah, but you can't do rise over run in 3D, unfortunately, Tim. It loses. You've got 3 things and you've only got 2 numbers. A ratio needs a top number and a bottom number, and you've got 3. So slopes don't work really in the usual sense. You can kind of turn them into 2D slopes. Right? It's much simpler than that.
Well, what you're looking for is that 3 and 6 add up to 9, which means
Yes.
that basically there's 2 smaller line segments add up to 1 more line segment. But I
Yeah.
also agree with what Tim was saying, is that you're not really doing rise over run, but what you do is you find the relative distance on each of the axes. So if you look at point A and point B,
Oh,
so
I know
point
what you're
B
doing.
is 3
Yeah.
minus 2, 4 minus 3, 1 minus 2, that's 1, 1, and -1. And you see if all the other
Right.
similar ones are proportional. So it could either be 2, 2, and -2, as long as they still have that same kind of
So what
pattern.
what Will is describing here is totally okay, but I won't call that a slope. What you're doing is essentially vectors. So you're looking at vector relationships in 3D. And actually in the next section, we'll do things like that, where you prove this using vectors. So
You could make those into 3 triangles based on the origin and then find out if they are equal relative to the origin, or we could go up and down an axis and see if they're equal to a point relative to those axes.
right, you could, if they were, you could, in the 3D world, you could draw a line like this and have your 3 points here, and therefore you would be destroying the 3-dimensionality to make it 3-dimensional, to do your slope thing, if that's what you're thinking, Tim. I'm trying to kill the word slope from your vocabulary in 2D. So let me give you an analogy of why I don't want you to think of slope anymore, even if you can construct ways around it to keep slope. I can see comfort zone in having that term. Imagine you're floating in space, billions of miles. Right, you've got an X, a Y, and a Z axis. To have a slope, don't you need an up? Which direction is up when you're floating in space? That's why you can't have slope anymore. Now you might say, well, Z is up. Well, that's just because we've orientated it in such a way that we think of it as up. But couldn't X be up if we just decided to orientate the XY axis and turn it a little bit? I mean, there's neither of the three axes is any more up than the other three if you're just thinking it as a mathematical concept. So keep slope to 2D world and go the other way. Can you do slope in 4 dimensions? Right, you've already lost it by 4. You could maybe fight with it in 3, but you'll lose it by 4. So you might as well just lose it, right? It's gone. Vectors are much better way of looking at things. Let's return back to the homework and see what we get here. Find the distance to a plane. We've talked about that. And oh, we're almost done. I've got a new guy. He appeared out of the blue. In 2D, if I said to you x squared plus y squared equals 9, what would you be looking at?
Circle.
Yeah. We agree center of the origin, radius 3. Now, if I said x squared plus y squared equals 9, but you were doing it in 3D, what do you think you'd be looking at?
A cylinder.
Well done. Yes. And it would be a cylinder that looks something like that. Wouldn't it be an infinite cylinder? I mean, there's no reason for it to go. What would, in 3D, what would x squared plus y squared plus z squared equal 9 look like?
Is that a sphere?
It is. I can't draw spheres. That's my closest. What would the radius of that sphere be? 3. Are we comfortable with the equation of the surface of a sphere is x squared plus y squared plus z squared equals 9? Now, if you move the center in 2D from the origin to say a point 1, 3, but the radius, we'll keep that as 3, won't the equation of the circle now turn into that guy? Are we happy about that in 2D? If you move over to 3D and you have a point 1, 3, 5, and we'll keep the radius as 3, the equation of a sphere, the surface of a sphere, center 1, 3, and 5, becomes that guy. Are we comfortable about 3D? You tend to get spheres from the equations that 2D would give you circles. And that kind of makes sense. Isn't a sphere just a 3-dimensional rotation of a circle? So if you are given the equation of a, well, let's work backwards. Let's suppose I tell you the center of a sphere is that guy. And let's say I tell you its radius is 10. Okay. Then the equation of that circle would be that. Agreed? And you get questions like that. Now the hard one. I want you to imagine this sphere inside a room, but the sphere is really big. Won't the surfaces, the XY plane, the XZ plane, and the YZ plane, won't they cut that sphere? Now, can you imagine that's the sphere I'm talking about? If you cut it vertically, what will the intersection of the surface of that sphere and that vertical plane look like? Won't it be a little circle? And wouldn't it be nice if we could find the equations of those circles? Because couldn't I cut it horizontally, which would be the XY plane, right? Or I could cut it at right angles and do a YZ plane or whatever plane I wanted. And we'd like to know that. So let's see how you find the equation of a sphere being cut by, let's say, the XY plane. Well, you take the equation. Just that guy. Isn't the property of the XY plane the same thing as just telling you Z equals 0? So isn't the XY plane just Z equals 0? Right? If you did it in GeoBraid, you'd see it. And since I know Z is 0 all the time when you're on the XY plane, won't this become X plus 1 squared, Y minus 2 squared, plus 0 take away 3 squared, which is 9, equals 100. And so this becomes X minus 1 squared plus Y minus 2 squared, 81 gives you 19. Can you see the equation of the sphere on the XY plane? So that would be, you took the sphere and you cut it with the floor. And what you'd see is a little circle. And this would be the equation of that circle. Does that make sense? How you can find the equation of any one of the three XY, YZ planes? What would an XZ plane look like? Tell me which variable would be 0 if it's an XZ plane.
Wait,
I have
why
a
is it
question.
9 squared?
Why?
Why is it 9 squared? Oh, ta-ta. I squared it and squared it twice. There we go. Fix it. Right. What is the XZ plane?
I think you mean 81.
Three squared is 9. 9 away from 100.
Oh, no, I'm sorry. I thought you were saying 9 squared was 91. I said.
Okay, right, we're good. Right, back to this question. XZ plane, what is that the same thing as?
Y equals 0.
And for completeness sake, what's the YZ plane?
X equals 0.
Have you noticed it's the guy that's missing is the clue here? It could happen that I do one of these questions, right? And I make, you know, the X0, the Y0, the Z0. So pretend I get a different question. And this is what I got. I got that guy. I got 121 equals 100. And when I tried to make it look pretty, I got that bad news. And that could happen, right? What? I haven't done anything wrong. You pretend I haven't screwed up in my adding and that, right? Different question. And that's what we got. What is that telling me about this sphere, right? The original sphere.
That it doesn't intersect with the plane?
Yeah. Can you imagine the sphere is so small it never gets to, well, it might not get to any of the planes, right? But it might not get to one of them, right? It might not make it to the XY plane, right? And that's okay. That can happen. What would happen, or what would this mean if this happened? So this means no intersection. Why is that? Oh, why? What would that mean? Right, it's been cut with the XY plane, and this is the resultant equation. That means it never cuts the XY plane, right? It's floating above the floor. What does that mean?
Would it be a tangent plane?
Not even a tangent plane, but the XY floor would be a tangent plane. Can you imagine that this is your guy and your sphere just touches the floor? In fact, wouldn't it touch the floor at the point 1,3? So we can look at spheres interacting with the three X, Y, Z planes, right? When they do, spheres make circles. Spheres never touch that plane, or spheres just touch it at a point. That makes sense that those are the three most likely visual situations. I'm just doing a quick scan through what's still going. Oh God, you wanted to talk about inequalities. So to finish with, let's show you some inequalities. And I'm going to pick the simplest ones I can think of. Would you agree that's the surface of a sphere of radius 3? What does that represent? That's
Wouldn't
only,
that be like a solid sphere?
say again, Molly?
Wouldn't that be like a solid sphere?
Yes, that would contain all the points inside and on the surface. That would be a ball bearing, wouldn't it? So if you wanted to do a, God, I forgot the name, a 3D printer of a ball bearing, wouldn't you tell it that equation, that inequality? If you only wanted to have a hollow surface, it would look like this. What would this thing look like?
It would be basically a really thick shell, because there'd be a sphere with radius 1 in the middle that had nothing in it. And
Correct.
then this inequality would be from that radius 1 to radius 9.
Right.
Or not, radius 3.
Yeah, I hear what you're saying. That's exactly what it would be. I had to draw it, but can you imagine a little a sphere with a hole inside? No, it's a hole, I guess, a spherical hole in the middle. Can you imagine that that might be useful if you wanted to manufacture a ball bearing, but a light ball bearing? If you figured out, as long as the hole in the middle is not too big, it's just as strong as any other ball bearing. Now, I can imagine very few people would want to do that, but do you know when you put things in space, doesn't every ounce count? And so if you know you can get a ball bearing, but it has to be a certain size, but you don't want to make it solid, wouldn't it be a cool idea if you could make it hollow? And wouldn't it be nice if you could then get a fancy metal version, because there are metal versions now that will make 3D printing with metal or ceramics or whatever you want. And now you've got a way of designing it. And for the last one then, how about this as a massive region?
Everything's out the sphere.
Yeah. Haven't I done with a very small equation the entire universe except for a little sphere of radius 3? That's kind of elegant, isn't it? The entire universe in one equation with a little hole in the middle.
Can I ruin something for you?
No, okay, go for it, Tim. Ruin it.
Hollow ball bearings are in fact a thing that are made for weight savings. They're commonly used in aircraft, and I've used them in racing hydroplanes.
I'll be honest, I didn't know that when I said that, but it's kind of cool that somebody did it. So it's not actually wasted. It's made me say, hey, see? People see that, and the engineers see that, and they think, hey, I could do my 3D printer and make a hollow ball bearing. I mean, I'm assuming that somebody did it first, right?
Well, so what they do is they take polystyrene balls, so like you know, that stuff that makes packing peanuts, and then they cover them in something heat resistant. I don't remember if they spray on, like there's metal that can be sprayed on, basically hardens like glue, and then eventually gets thick enough that they can put actual metal on it. But they work pretty well because what makes something strong is actually that last outer shell. Like if you have a shaft, that last, it's the surface, or it's the surface area of the end that makes it strong, that like the outermost bit. So like adding a small amount on the end of the radius makes it much, much stronger because the cross-sectional surface area increases with R squared, and you're only adding like R thickness. So, and you're getting R squared benefits. So hollow things actually are super awesome for making things strong and light.